Uh, we know that the drag, if you are swimming in the water and when you are walking inside the water and you are walking inside the air, which is basically what we are doing now. When I'm walking like this, actually I'm walking within the air, right? The air is here, everywhere. So it will be different. The size, the velocity as I move, the faster we move, the higher the friction. Okay. Not this tutorial. On Tuesday afternoon tutorial, I show some of you the cases of MAN truck. Okay. In the MAN truck presentation, they told you that after some speed, right, the friction due to the rolling of the tire will be much lesser compared to the friction due to the air. Okay, if you have time, we can go through that video later. So basically, it depends on all those parameters: the shape, the orientation, and so on. Okay, so from those parameters, we know that will be boil down to one parameter called Reynolds number. Right? So let's take a look at the cases of a disc. Okay. See, this one is your disc. This is your coefficient of drag. Okay, someone has done it. How do you get it? From experiment. Okay, and you will do one of it. You will do one of it. I do not know whether you have done it or not. We have wind tunnel there. Okay, please take good care of it. Okay, 2 semesters ago, one student do something on it and the computer just burst. Yeah, and this computer is very old, so we need 6 months just to get the component, right? So be careful with that, be gentle with that. Okay, our equipment is quite okay. It's quite good, right? But it's already 20 years old, right? So be careful with it. Right? Be gentle. Follow whatever HSE is needed, right? So that you can do the. Okay, so if you do for a different speed of the fan, right? This different speed of the fan means different flow. Then you will get the drag force. The drag force. You know, from those, you got the load cell, right? Any one of you has seen it? The load cell, where you put that thing there, you put everything there. This load cell will measure the drag and the lift. The lift can be positive or negative. The drag can be positive or negative, which means it's always pushing to that direction. Okay, so from that you will get your FD. If you get your FD, you can calculate your CD, right? Because you know FD is equal to CD times half rho V square. So you can do that. Okay, so they do that and then they got this. Okay, what do we see from here is you get several regions. The first region is this very low Reynolds number region. Okay. Have you tried to pour an oil on a paper or on a kind of surface? What do you see? You compare it with water. You pour at the surface like this plate, right? You pour it here. What do you see? It start to roll at very slow speed. So those kind of thing, those kind of very slow movement is called this creeping flow, which means the flow is creeping, slowly moving, sluggish, right? Just like a snail moving. Okay, so in those low Reynolds number, you can see here that the CD is a strong function of Reynolds. As the Reynolds increase, the CF decrease. You know why? Because you see, even in your CF, you remember your CF is a function of Reynolds number, right? 64 divided by Reynolds. So it is a strong function of Reynolds number. Okay? Then you get something going up again. This is the region where you have to be careful because increasing the velocity, right, we're not decreasing the drag coefficient, but increasing. Until some point, it will decrease again, right? This one is the moderate range. Okay, this is where the Reynolds number is still plays an important role. But in the turbulent region, you can see that it is not a function of Reynolds number anymore. Okay, so at some point, Reynolds number does not play any role. Okay, so the inertia effect is only important when the Reynolds number is small, right? When it is big, there is nothing to worry about. Okay? So you can see here that at the very low Reynolds number, the shape of your body does not play important role. I mean, it's not so significant, but the Reynolds number, yes. Sphere and hemisphere and circular disc, all of those has about the same CD, right? The CD is 24 over Reynolds, 22.2 over Reynolds, and 20.4 over Reynolds. Even though the shape is totally different, but they are not really affected by the shape of that, right? So it's more into the Reynolds number, okay? So that the shape does not have a major influence on the drag coefficient. Okay. This one is important for my student, but for my master and FYP student. So if you want to take FYP with me, no, I'm too confident. You need to learn this one. Okay. So this term, the Navier-Stokes term that you have before, right? This term is called inertia term. This one is the transient term. This one is the convective acceleration term. This one is the pressure, viscous, and gravity term. Every single those things will play important roles. When you are having a high Reynolds number, this one becomes less important, but this one will become more important. Okay? Now, that one if we are having a low Reynolds number. What happens if we have a high Reynolds number? Opposite. When you have a high Reynolds number does not play an important role, but the shape of your body will determine the drag coefficient. You can see you have the same hemisphere. You have the same. Okay, assume this one is your hemisphere. It's like a cat toy. So if the air is coming from here, where you have the concave or convex? Yeah, the up to you lah, convex. Okay, convex. You have this, it will be much lower as compared to you have that. That's why you see your side mirror is having those not in the opposite direction. Can you imagine if your side mirror is having the right? What will happen? I don't know. I haven't tried. You should try if you want. Right? So in that case, you can see different in the shape or orientation. It gives you quite big difference. See, if you have the air on the plate, on the flat plate, on the flat component of it, the drag coefficient is 1.2, which is three times higher than the top one, where your air is coming on the convex surface. So you see that for a different Reynolds range, the behavior of the drag coefficient will also be different. Which component more important will also be different. So you need to Look at it.